now.
Yes, I got it.
Can you got it? Did you
Yes.
get it?
Yes.
All right. All right. Okay, folks. Good morning to all of you. I see there are 28 participants. That's about the class strength. So I assume that everybody is in. I just want to be some kind of an interactive session. So it's not like me talking all the time. I also want to see if you were able to, for example, see my files in the Canvas. Did you get the types of nuclear reactions, folks? Yeah, I would like to hear a voice thing.
Yes.
Good.
Yeah.
So what I also have done essentially is to give you a voice-over presentation in Kaltura. So kind of you have two files, I believe. One is the PDF file to go over the presentation. The other one is a voiceover. So were you able to listen to the voice there when you open the files?
Yeah.
The reason I'm asking all these stupid questions is because this is the first time in my life I'm teaching through this. I just want to make sure that everybody is able to, access the files. This morning, I also uploaded some files on the atomic structure too. So before I continue with this presentation today, I just wanted to know if you guys have any questions on the types of nuclear reactions that I have posted. Anything that's not clear, including the Big Bang theory and all that stuff. Any questions? Are we okay? All right. Can you all see the board that I have behind me? You see a circle and a dot in the middle?
Yes.
Okay. Great, excellent. So what we're going to do today is, I think I sent you a presentation on the quantum theory, but sometimes, when you're doing mathematical treatment, we sometimes lose the big picture of it, exactly what quantum is. So today, we're going to look at the physical meaning, not the mathematical meaning, but the physical meaning of quantization, and more importantly, the Bohr's model of hydrogen atom. We all know hydrogen has one proton in the nucleus and one electron in the outer shells, correct? And that electron is in the 1s subshell. We'll get into all those descriptions in a second, but what we need to understand here is, if I have a positive charge here and an electron here, can you all see the board here? I put a P in the center and a E, that is an electron that is rotating, right? So the question sometimes you may have is, why not this electron get sucked into the nucleus? Because positive attracts the negative, right? So you have a negatively charged particle and you have a proton. So why can't the electron jump into the nucleus? Why does this happen?
Is it because it doesn't have the energy to do so?
Right. Nuclear reactions. Remember, we talked about electron capture, right? It requires a lot of energy. The second most important thing is, the argument that the electron should jump into the nucleus is valid only if the electron is static. That is, if it is just staying there doing nothing. But that is not what an electron does, according to Bohr. Just like the planets keep on rotating around the sun, what Bohr proposed is that this electron rotates around the nucleus. So by virtue of the rotation around the nucleus, the electron will have what we call a centripetal force that kind of moves it away from the nucleus, right? So here there are two things that are very important to keep in mind. Number one is, there is a Coulombic force between the proton and the electron, right? That is the force which allows the electron to get attracted towards the nucleus. And then there is a centripetal force which kind of keeps the electron falling into the nucleus. Now, for the electron to stay in the orbit, then the Coulombic force of attraction should be exactly equal to the centripetal force that the electron has. Would you all agree with that, folks? So as long as the Coulombic force, that's the force of attraction between positive and negative, as long as that force is exactly equal to the centripetal force is because of the force that is associated with an object rotating in a circular fashion. right? So now if you look at these two things, on one hand, do you all know what a Coulombic force equation is? Force of attraction between positive and negative? You must have done it in high school physics, right? Coulomb's law. Coulomb's law tells us that the force of attraction between a positive and a negative is proportional to the product of the charges divided by the square of the distance it is separated by, right? That is what a Coulombic force is. Now let's assume that electron has a charge. And would you all agree that the charge of an electron exactly equals to the charge of a proton, except the sign is different, right? So the charges are equal. So if I call the charge of the proton is E plus and E minus, both are E's. So when you multiply them, that will be E squared. That will be the product of the charges, because we have two charges. They are identical in magnitude, divided by the square of the distance. So the distance between this orbit and the nucleus, if I call that r, small r, then E squared over r squared equals to the force of attraction. Can you all see that equation on the top of the board? Okay, if you cannot see anything, please shout out, because I can't see much from this computer here that I have. Now, anyone knows the equation for the centripetal force? Let's assume that the electron has a mass of m, rotating with a speed of v in an orbit of r. In terms of the mass, velocity, and the radius of the orbit, what is the centripetal force? Any thoughts on this?
mv squared over r.
Absolutely wonderful. That's absolutely correct, Joseph. That is mv squared over r. So as long as this condition is met, that is E squared over R squared equals mv squared over R, then we know that the electron will stay in orbit. If mv squared over R is greater, then that electron will be ejected out. If the Coulombic force is stronger, then the electron will collapse into the nucleus. As long as these two forces are equal, would you all agree that the electron can stay in the orbit? Right? So now if you look at this equation, what you find is you have an r here and r squared. If you multiply by r both sides, right, then you will have an equation that basically tells you that r equals E squared over mv squared. I just rearranged that mathematical equation. I didn't do anything. Basically, I multiplied both sides by r, divided both sides by mv squared. That will solve for the r. So this is how Bohr thought that the radius of the orbit and the velocity of an electron are related. But the problem is he could not solve this. You know why? Because we have no idea about the size of this radius, because you cannot go into an atom with a ruler and try to measure the distance between the nucleus and the electron. That is just not possible. So what happened was there are two unknowns in an equation. As you all know from math, if you have an equation that has two unknowns, there is no way you can solve it, correct? I'm sure you agree with me, right? So there is no way you can solve this equation because you have R and V, two unknowns. In fact, this is where Bohr got stuck. So how do we resolve this crisis? Okay. As you all know, as Bohr was working out these things, there have been several other phenomena that have been discovered, just like E equals mc squared, right? De Broglie suggested that anything that has a mass, and if it moves, de Broglie said that particle should behave like a wave such that the wavelength of that wave, lambda, equals h, that's the Planck's constant divided by m times v. You all know about this equation, right? You must have seen that in the physics or the chemistry 1 classes. So the wavelengths associated with the particle in motion can be solved by looking at h over m times v, where m here refers to the mass of an electron, which we know is about 9.1 1 times 10 to the negative 31 kilograms that has been established. And h is the Planck's constant. You all know Planck's constant, 6.626 times 10 to the negative 34. And v is the velocity. When you are using this equation, I want you to keep in mind that you have to use SI system of units. The reason for that is the Planck's constant is measured in joules times seconds. Joule is a SI unit of energy. The mass has to be kilograms. A lot of times students make a mistake because they are not using the right units. So in SI system, the mass has to be always in kilograms, and the velocity here should be in meters per second. When you plug those numbers properly, then you know the wavelength of that particle. In other words, that is the wave-like behavior, anything that moves. So if you are watching the US Open tennis, you can see the ball moving with a speed, right? Now, if you know the mass of the tennis ball, and if you know the velocity of the tennis ball, you will then be able to calculate the wavelength associated with that tennis ball in motion, right? By knowing the mass in kilograms, the speed of the ball in meters per second, plug that in, it will tell you. In most cases, what happens is you have a very small wavelength. In fact, the tennis ball, if you calculate all this stuff, you will get a wavelength of about 10 to the negative 27 meters. It is such a small wavelength that you will not be able to physically see. It is there, but your eye resolution is not enough to give you that kind of a wave behavior. However, if to increase the wavelength, we can reduce the mass, right? Or reduce the velocity. In both cases, you will see an increase in the wavelength. So you can manipulate the wavelength just by changing the velocity. If you can't change the mass, then keep the mass constant, but by playing with the velocity, you should be able to generate different wavelengths. So that is the concept of de Broglie. I want you to again go back into your textbooks and read about these things in detail. But if you have any questions about this, you are most welcome to interrupt me anytime, unmute your microphone and say, sorry, I don't understand this. I'm not going to find fault with you because we are all learning in a very different environment here. So don't feel bad. Just ask me and I'll try to maybe give you a more detailed example. Okay, so here is the beauty of this. I want you to follow this argument very, very carefully. Now, if an electron is rotating around the nucleus, right, that electron should have a wave. That wavelength of that wave should be decided by the de Broglie's equation, lambda equals h over mv. So in other words, there is some kind of a wave here that is associated with the electron. Now, this is a closed loop, right? So the wave should be exactly in phase. If it is out of phase, this wave will not be complete. So in other words, this wavelength of this wave cannot be any arbitrary number. Would you agree with me? To understand this a little bit more, let's do a thought experiment. Okay, let's say this is my radius here. I take a pair of scissors, and then what I do is I open up this circle. When I cut this circle, straighten it up, what do you get? What kind of a geometry you have?
Line.
You have a line. You're absolutely correct. So let's look at that line and then argue about the wavelengths. All right, so that is the line that you get. This is the line that we got by cutting this circle and making it a straight line. Now, in terms of the radius of the circle, can you tell me what should be the length of this line? The length of this line should be exactly equal to the circumference of the circle, right?
2 pi times the radius.
That should be equal to 2 pi?
Times the radius.
2 pi times radius, correct? So in other words, the length of this line is 2 pi r. Because I cut this from a circle, the circumference of a circle is 2 pi times r, which is the radius of the orbit. Because I cut this circle and straighten this up, this length L here should be equal to 2 pi r. Would you agree with me?
Wait, didn't you say that it's a wave?
No, we'll talk about the wave now in a minute. I'm just
Oh,
now
okay.
looking at the total space available for the wave.
Okay. Mm.
Now, a wave has to be on this line here because it was in the circle previously. Now we are trying to look at, suppose if I have a wave like this. Is that acceptable? When you close the line again, the wave has to complete itself, does it? I think it does because a wave has a crest and a trough. So this point here, basically, let me put this one again a little bit more carefully here. I'm trying to draw here. This wave completes itself because I have a crest and a trough next to each other, right? So that is acceptable. So what is the length, wavelength of this wave? We can say it's lambda, right? Yeah, so we can say this is acceptable because 2 pi r equals lambda. Let me tell you what is not acceptable. Let us say if I have a line like this and only part of the wave. Can you see this line now? When you fold this line back into the circle, do you think you will have a complete wave? No. So in this case, the wavelength is not some kind of integral multiple of the length of it. So this is not acceptable. So whatever wavelength this wave has cannot be acceptable because it does not close the wave in the circle. We'll take you a few more examples of it. Basically, I'm trying to convince you that you cannot have any arbitrary wavelength of that wave. It has to be certain wavelengths. Let me give you another example of what is acceptable. Let's say if I have something like this. Is that acceptable?
Yes.
It does because I have the displacement here, right? I have the trough here and the crest there. So when I fold it, a crest and trough will come next to each other. That's what a wave looks like. So in terms of lambda, what should be the wavelength of this wave then? In the previous example, we put lambda, right? Now, in terms of lambda, what is the wavelength here?
2 lambda?
How many wavelengths are there here in this space here now?
2.
You are absolutely correct. Wonderful. So 2 pi r equals 2 lambda is also an acceptable solution. Let's look at another one. Let's say I have a wave like this. Is that acceptable?
No.
Yeah, I don't think so.
So what is the wavelength in terms of lambda here for this wave?
Is it 3/2?
Lambda, right?
Yeah, it's 1.
From left to right, up to this point, it is lambda. And then I have only half a wave, correct? In other words, the total wavelength for this is 1.5 lambda. Would you agree with me?
Yeah.
Is 1.5 lambda acceptable? No.
No.
1 lambda is okay, 2 lambda is okay, but 1.5 lambda is not acceptable because when you fold this line into a circle, you are putting 2 crests next to each other. So that does not satisfy the definition of a wave. A wave has to have a crest and a trough next to each other, correct? So for that reason, this is not acceptable. In fact, we can say as long as the wave, you know, like you can have any wave, the trough and the crest, if they are next to each other, that will be fine. So what is the wavelength of this? That is 1, 2, 3, 4, 5, 6, about 7 lambdas. So we can say 2 pi r equals 7 lambda is acceptable. So you can squeeze in any wavelengths as long as I now give a condition 2 pi r equals n lambda, where n can be a whole number, a positive number. It cannot be a fraction. Would you agree with me? So in other words, this wave is satisfied if n equals to 1, 2, 3, 4. You can go all the way to infinity, I don't care. The only thing you cannot have is a fraction. Cannot have 1.5, 1.2, 1.3. So that is where the discreteness comes into the picture. This is the origin of quantum behavior. You see, very simply, we can see, because just by looking at the properties of the wave, we know clearly that not all wavelengths satisfy 2 pi r equals n lambda. Only waves that satisfy this, where is n equals to a whole number, a positive number, an integer, not a fraction. It cannot be 0, it cannot be a negative number, because wavelength cannot be negative, right? So that is how he has done this. This gave hope to Niels Bohr. Watch this very carefully. But before I continue, are there any questions up to this point?
I have a question.
Yes,
So
sir.
if the electron moves around in its orbital in a wave-like fashion, right?
Uh-huh.
If you look at it from the perspective of a sphere, how would that vary? Like, would it only move like up and
A
down? Or would it
sphere
have
basically have to
helical?
translate this whole argument into a three-dimensional space, but still that works.
But how would it work? Would it be more of like a helical fashion rather than
Yeah,
just
it is a
up and
helical
down?
fashion, yes.
Okay, thank you.
Yes, that you're absolutely correct. But whatever it is, when you define an orbit, right, within that sphere, the orientation of that orbit may be different in a sphere, but the argument for a circle still holds good. So it still has to be 2 pi r equals n lambda. Is that okay, Joseph?
Yes.
Great, excellent. All right. Now, Niels Bohr got a breakthrough that he was looking for. When you have this argument 2 pi r equals n lambda, then I can say 2 pi r equals n, but de Broglie said lambda, which is the wavelength of the wave associated with the moving particle, must be h over mv, correct? So this should be nh over mv. Would you agree with me? All right. Now what I'm going to do is I will multiply both sides by v and divide both sides by 2 pi r. When you do that, the v equals nh over 2 pi mr. See how beautiful this equation is, right? So the velocity of a wave then equals to n, it could be 1, 2, 3, 4, depending on which orbit it is, and times the Planck's constant divided by 2 pi m, which is the mass of the electron, times the radius of the orbit. Now you have two equations. You see that first equation, r equals e squared or mv squared, and I have another equation where v equals nh over 2 pi mr. So I have two equations and two unknowns. And mathematics tells us that if you have two unknowns and two equations, you should be able to solve. Is that correct? That's what we were told. If you have one equation with multiple variables, you cannot solve it. But if you have two equations and two variables, then you should be able to do that. So how do I do this? Now that I know v equals nh over 2 pi mr, I can take this, put it back into that equation, which is r equals e squared over mv squared. Let's see how that works out then. So in that case, r equals e squared over m times nh over 2 pi mr squared. Right, folks? Great. So I'm now going to open this up. Simple math tells us that r should be equal to, let's see, 4 pi squared, m squared, r squared, e squared, divided by m n squared h squared. Okay? So basically, I took the denominator in the fraction here, put it up there. That's all allowed by the math. So now I have an equation which says r equals 4 pi squared m squared r squared e squared over m n squared h squared. So I have a mass here and a mass squared there, so I can cancel that. That becomes only mass. And I have an r here and an r squared there. So if I divide both sides by r, this becomes 1 here. And now you can solve for the r. R then should be equal to n squared h squared divided by 4 pi squared m e squared. Do you see the point here? So what is happening now, by knowing the orbit size, first orbit, second orbit, third orbit, and by knowing the Planck's constant, 4 pi squared, mass of the electron is known, 9 times 10 to the negative 31 kilograms, and charge of an electron is also known as 1.649 times 10 to the negative 19 coulombs. These are all known quantities. So once you plug for h, m, and e squared, right, you get an equation that says r equals, let me write this clearly, r equals, when you plug those constants there, you get 5.29 times 10 to the negative 11 n squared in meters. So what is this telling us? This Bohr's model is telling us that by knowing the value of n, you can plug in different values of n into this equation. You know exactly the size of the orbit. So what is the distance between the nucleus and the only electron in hydrogen then, in the ground state? So for that, n
Professor
equals
Chari,
1, right? Yes.
what do you have written at the very bottom? The n equals at the very bottom.
I'm sorry, which one is this?
So at the very bottom, or the r equals, I'm sorry, the very bottom. Yeah, that.
Yeah.
What does that say?
N squared h squared
Okay.
divided by 4 pi squared m e squared.
Okay, thank you.
No problem, it's okay. I have a small space here to adjust the teaching, you know. Like in a big classroom, we can write everything, you know, from left to right in the whole yards. So please, anytime you have any questions, stop me. All right, good. So this equation is the first time we knew the distance between the nucleus and the electron and hydrogen atom. And this surprisingly 5.29 times 10 to the negative 11 exactly meters. So this is why Bohr's model is so successful. This is the reason why he was given the Nobel Prize. For the first time, humanity knew the distance between the nucleus and an electron from simple physical forces like Coulombic forces, centripetal forces, de Broglie's equation, and the conditions for the wave within the orbit. We were able to derive this. Is this clear to all of you?
I have a question, Dr. Chari.
Trevor, go ahead.
So you said this is for like the distance between the nucleus and the electron in the ground state, right?
Correct. That's the ground
Okay.
state. Yes.
Okay.
You can excite them, but again, you always have to have a discrete energy levels. We'll talk about the energy in a second.
What would these units be in like for the answer? Like if you were to plug in an n, what would like the units be in for the distance?
I wrote it here. It is always in meters
Meters.
because we use SI units right here for the Planck's constant, the mass in kilograms, Planck's constant in joules second, right? And the charge is in coulombs. So when you put all the SI units, the distance will have units of meters.
Okay.
Does it answer your question, Travers?
Yes, thank you.
Excellent, wonderful. All right. Any other questions before we move on to, I know the position of the electron now in an atom. Keep that in mind. I'm using the language which becomes very, very important as we move on. I use the word position, right? I know the position of an electron in an hydrogen atom according to Bohr. That's great. And this is not a disputable quantity. There is no argument here. Everybody agrees with this. For hydrogen atoms, we know the distance between the electron and the nucleus, right? So that's a very small space, agreed. But still, we know accurately what the distance is. The next thing is, okay, if I know the distance, the next thing is, what about the energy of this electron? What is the stabilization energy of this electron? Right, there is a Coulombic force and there is a centripetal force too. So we can use the Coulombic force and then try to see if we can calculate the energy of this electron. All right, so let me erase this part of the board and get to the energy. So we know the force equals E squared over R squared. That is the Coulombic force, right? How is force converted to energy? Anyone knows? How is force related to energy? Simple physics, right? How are force and energy related? Energy equals force times what? Isn't it force times distance?
For work,
Yeah?
yes.
Joseph, agree with me?
Yes.
Force times distance is your energy, right? You all have done Calc 1 or 2, right? So, because you're good at calculus, so I can perhaps say the energy here equals to integral force times distance, dr. That makes sense? Yeah? So I can say energy equals integral E squared over R squared times dr, where E is the charge of an electron, which is a constant, R is the distance, right, between the nucleus and the electron. What is the integral of E squared over R squared dr? Anyone remembers?
Is it
What is
negative
the integral
E
of x squared
squared?
dx? Remember? It is, if it is integral of x to the n dx, the formula is x raised to the power of n plus 1 divided by n plus 1, right?
Yeah, so wouldn't it be negative E squared times
By r.
R to the negative, or divided by R?
Would you agree with me? That is simply r to the negative 2, right? R to the negative 2 plus 1 is negative 1 divided by negative 1. That makes it E squared over r. Yeah? But we already know what r is from the previous derivation. So we can now then say E energy equals negative E squared over r, but then E equals negative E squared over, remember we said it was n squared h squared divided by 4 pi me squared. Correct? So in other words, this becomes negative 4 pi m e to the 4 divided by n squared h squared. Correct? So in other words, as the value of n increases, what happens to the energy? It becomes less positive, less negative, right? When we say less negative, that means energy is getting higher. So if n is very small, this is a large negative number, but if n is large, it's not going to be a large negative number, but a small negative number, which implies that the energy goes up in energy. So as you increase the n, the energy value becomes more and more positive. In other words, the energy of stabilization decreases. More negative the energy is, more stable the electron is. That means that is your exothermic process, right? That is energy released by keeping the electron in the orbit. If that energy is large, that means that's energy of stabilization. So this electron in the hydrogen is stabilized in n equals to 1. So you can calculate this number. Now, we already know from Planck's equation, what is energy in terms of Planck's equation? Anyone remembers that? E equals what? Remember Planck's equation? What did Planck say? The energy of a wave depends only on the frequency, not the amplitude, right? So remember, E equals h times frequency of the wave. So this is basically E equals h nu. Frequency, as you all know, is velocity divided by wavelength, correct? So this one simply hc over lambda. Would you agree with me? All right. So now what I can do is I can use these equations now. Hc over lambda equals negative 4 pi e squared or n squared h squared, and rearrange to write the value of 1 over lambda. When you do the 1 over lambda value, it becomes 4 pi squared m e to the 4 divided by c h times h is h cubed times n squared. Am I making sense here, folks? So if I know, yes.
Does that say me squared, right, on the last equation?
No, but in the last equation it was e squared here, right?
Yeah.
If you can see the board, but there is a e squared term here too.
Okay.
So when you rearrange them, e squared times e squared becomes e to the 4th.
Oh, you do the 4th. Okay, thank you.
Yes. So that's where this one value comes in. You see how beautiful this is. In
Right
about 5
behind you.
minutes, I'm going to take you from this equation to an equation that you all have known.
Right behind you, that's Planck's equation, right? Like on the right side there.
Trevor, yes?
I was trying to see if that was Planck's equation there. You said you were asking for Planck's equation.
Yeah, Planck's equation is on the right-hand side. In fact, there was Planck's equation is E equals h times nu, right? Frequency. But frequency is defined as velocity over the wavelength. So h nu can be written as hc over lambda. Then I solve for the 1 over lambda value. When I get 1 over lambda, I get 4 pi squared m e to the 4 divided by ch cubed times n squared. Right? So
Yes.
one of the beautiful aspects of it is, if you look at this equation very carefully, everything is a constant except the n value. Is that correct? You have 4 pi squared m e to the 4 divided by c, which is the speed of light, times cube of the Planck's constant times n squared. The only variable here is n. Would you agree with me? So if I have a nucleus and two orbits. You can see orbit 1 and orbit 2, right? So if an electron goes from orbit 1 to 2, it absorbs energy because orbit 2 is less stabilized. On the other hand, if an electron in the orbit 2 jumps into orbit 1, it releases light. This is the basis for atomic absorption and emission spectroscopies. Absorption is when electron goes from a low level to high level. Emission happens when the electron comes from the high level to the low level. Correct? Now, this is purely based on the orbit size. N equals to 1 is a smaller orbit, N equals 2 is a larger orbit, correct? So we can then conveniently say, if you look at this equation, 4 pi squared me to the 4th divided by ch cube, right? And 1 over lambda is proportional to 1 over n squared here. The beauty of this, when you calculate this constant, it turns out it's approximately 1.09 times 10 to the 7 meter inverse. That is, when you put the pi, m, e to the 4, velocity, Planck's constant, the normalizations, when you do all this, you get this. And 1 over lambda then equals this times 1 over nf squared minus 1 over ni squared. So if there are two energy levels, n equals nf and ni, nf is the final level, ni is the initial level, right? So the wavelength of the light emitted when an electron jumps from initial level of I to final level of f, the wavelength of the light emitted is 1 over lambda, can be calculated using this equation. You have done this lab in Chem 1. Remember the Rydberg constant and all that stuff, the atomic emission spectroscopy, calculating the wavelengths based on the orbit size. We didn't teach you all that stuff at that time. We just threw the equation on your face and asked you to deal with it. We never gave you the origin of why this equation works. You know, these equations were not emailed to us from the planet Mars, right? We have worked out, this is how all these equations are worked out. So sometimes what they do is, okay, in the beginning, just use this equation. Then you start wondering, why does this equation work? Now you have the basis for telling people, this is the reason why this equation works. And in fact, it predicts the spectral frequencies or the wavelengths in the atomic emission spectra of hydrogen atoms so accurately. Okay, remember the Bose-Balmer equation, that's what we talked about. In fact, this equation was empirically suggested by Balmer, but there was no explanation of why this equation works at that time. It was Niels Bohr who worked out all the logistics and did all the calculations that I showed you a few minutes ago to come back to this equation and convince people this is the reason why this equation works. It's amazing. The brilliance of Niels Bohr, there are so many videos also of him. If you want to watch YouTube, you get addicted to Niels Bohr's intelligence. He's one of the smartest guys you can ever think of. And, you know, there was no wonder he got Nobel Prize for this. Okay. Now, in the textbook, you have some problems. But before we get into the problems, we also need to understand a couple of things. You all know lambda has to be a positive number, right? Wavelengths cannot be negative, correct? So what are the conditions for NF and NI for it to be positive? Is NF should be greater than NI or smaller than NI?
Greater?
Hmm?
Shouldn't NF be greater than NI?
If NF is greater than NI, right? Then what happens? 1 over NF becomes a smaller number, right?
Oh, the other way.
Other way around. Good.
Yeah, it has to be smaller.
It has to be always smaller, right? So when the electrons fall from higher levels to lower levels, so we have, let us say, these are all the orbits. Can you all see the board, the orbits, right? 1, 2, 3, 4, right? If an electron falls from 3 to 2, right? So what should be the Ni value here? The initial level is 3, and the final level is 2.
2.
So this is where you put those numbers in. And once you do this, you're going to get a positive number, and you get a wavelength of lambda right there. What surprisingly Balmer figured out was anytime an electron falls to level number 2, no matter where the origin level is, you can have 15 to 2, or 10 to 2, or 3 to 2, 4 to 2, 5 to 2, it doesn't matter. Whenever an electron jumps from a higher levels to level number of 2, the wavelength that is observed falls in the visible light. So that's about 300 to 600 nanometers, right? The violet, the indigo, the blue, the green, the yellow, the orange, and all that stuff. You all know that spectrum, color spectrum, right? So that happens only if the electron jumps to level number 2. On the other hand, if the electrons jump to level number 3 or 1, you also get light, but unfortunately that light will not be visible because the frequencies or the wavelengths of the light emitted are either below the visible wavelength, which is what happens when the electrons jump to level number 1, or above the visible light, that happens when the electrons jump to level number 3. So only those emissions that originate at a higher level but terminate at level number 2 gives off the light that is visible. So that's how Balmer's equation works. Balmer's equation is always given as 2 there, as it works for the visible light. Am I making sense here, folks? Does that help you? Because the textbook does not give you all these details. So I thought I will fill it up so this way you'll have some confidence in how these equations are generated. But in the exam, you don't have to memorize these equations. If there is a question about the atomic emission spectra, we will tell you the equation, and we'll also give you the numbers. For example, we'll ask you, find the wavelength of the light emitted when an electron falls from level number 4 to level number 1. So that equation is there with you. You plug those numbers, you know, the final level is 1, initial level is 4, plug it in and solve for the value of lambda. Sometimes lambda is, in this equation, you get the lambda in the units of meters, but sometimes they also use the lambda in nanometers. You know, so for example, it is 350 nanometers, which is 350 times 10 to the negative 9 meters. Okay, you should be able to convert meters to nanometers in this case. Are there any questions up to this point?
Dr. Chari.
Yes, Trevor.
So it's probably like straightforward, but like when you're talking about the levels, like with the orbits, those are just like the orbitals, like SP, D, and
No,
F,
no,
right?
they're not the SP. SP are basically subshells. They're not the shells. We'll
Okay,
talk
so it's
about that in a
different.
minute. Yeah.
Okay.
So within the shell here, right? This is shell number 1, shell number 2. Within these shells, you have the subshells. Those are your subshells like S subshell, P subshell, D subshell, and all that.
Okay. So they're unrelated, like when we're talking about this topic right here.
Yeah, we will talk about that too. In fact, if you look into the slides that I have uploaded in the Canvas, in the atomic structure, you do see all those shapes and orbitals and all that stuff.
That's in week 2, right?
Yeah,
Okay.
that's the chapter chapter 1 itself, but we spent little time on nuclear reactions because that is very important for those of you who are writing GREs. And I heard that you don't learn about nuclear chemistry in any of these courses, neither in Chem 1, Chem 2, or Quant, or Biochem, or Organic, right? But unfortunately in GREs, these questions are always there. And I just want to give you a heads up on those things, how to deal with the nuclear processes, all right?
Hmm.
And then this is, again, this is something the textbooks don't talk about. So I thought this information may be useful for you to think about and then see how people derive these equations. Trevor, is that okay?
Yeah, thank
Okay,
you.
great. Okay, we'll move on, continue with this. And the next question that we have is, Bohr's model was good for hydrogen atoms. So I'll tell you where Bohr was very successful. Hydrogen, no problem. If I have helium plus ions, it works. Lithium 2 plus, it works. Beryllium 3 plus, it works. But if you look at helium atom, there's a problem. What you calculate and what you observe are different. Similarly, when you look at lithium, lithium metal doesn't obey Bohr's theory, but lithium 2 plus obeys Bohr's theory. Similarly, beryllium. Elemental beryllium does not obey Bohr's laws, but a triply positive beryllium adopts the Bohr's model. So what do you conclude from this, folks? What is common between the species that obey Bohr's law?
They can only have one electron.
Hmm?
They can only have one electron.
Absolutely correct. Great observation. Wonderful. So helium plus has only one electron, lithium 2 plus has one electron, beryllium 3 plus has one electron. So Bohr's model works so beautifully for all the systems that have one electrons. So if you now look at all these one electron systems, in which of these species this electron is tightly held? They all have one electrons, right? Hydrogen has one electron, helium plus has one electron, lithium 2 plus has one electron, beryllium 3 plus has one electron. Do all electrons have the same energy or do they have different energies? What does the common sense tell us?
Different.
Should be different, right? And the difference because?
Different end.
Although they all have one electron, but don't forget the nucleus, right? In the nucleus of hydrogen, we have only one proton. In helium, how many protons we have? 2. In the lithium, we have 3, right? So the energy of an electron is basically proportional to what we call Z squared over N squared, where Z is the atomic number, that is the number of protons in the nucleus, divided by N, which is the shell number. There should be, of course, a negative sign here because that's the energy of stabilization. All right? So, suppose if I want to calculate the energy of 1s electron of hydrogen, what should that be proportional to there in the ground state? What is the Z value? That is the number of protons in hydrogen is what? Is it 1? Atomic number of hydrogen is 1, right? So that is 1 squared over n squared. N is the first shell, so it's 1 squared. Compare that now with the energy of 1s electron of lithium. Lithium, atomic number of 3, that should be proportional to Z, which is atomic number is 3, that is, of course, 3 squared divided by 1 squared. Right? If I take the ratio of these energies, we get energy of hydrogen 1s over energy of lithium 1s is going to be 1 squared over 1 squared divided by 3 squared over 1 squared. So what should be the value then?
1/9.
1/9? That is about 1/9. Or we can say the energy of 1s electron of lithium is 9 times the energy of 1s electron of hydrogen. Does that make sense, folks? In other words, we know the one electron of lithium 2 plus is held 9 times stronger than the electron that is held in the hydrogen atom. So which one is it to remove? Hydrogen 1s electron or the lithium 1s electron in the lithium 2 plus?
Hydrogen.
The hydrogen is easier. To pull out the electron of the lithium, you need to spend 9 times the energy. In general, people know that this energy here, energy of the 1s electron is constant. So energy of the lithium 1s is 9 times. This is 13.6 electron volts.
Professor Chari,
Yes,
I have a quick question.
sure.
So up at the top of the equation, you said that the energy of an electron is proportional to z squared. Is that over n squared?
Mhm.
And what is that like? What does the n represent again? I just wanted
N
to
is the
clarify.
orbit number. First shell, second shell, third shell. Orbit size.
Okay.
The same n, remember in the past when we calculated the radius of the orbit, right? It's 5.29 times 10 to the negative 11 n squared.
Mm-hmm.
N is an orbit number 1, 2, 3, 4, so on and so forth.
Okay.
Does this still work for different isotopes?
Hmm?
Does this still work for different isotopes?
Great question. See, the issue with the isotopes is only the mass of the nucleus, right? Not the charge of the nucleus.
Mm-hmm.
So in principle, yes, it should. So whether you have hydrogen or deuterium or tritium, the difference only is in the neutrons, right? Neutrons do not exert any Coulombic force on electrons because neutrons have no charge. Am I making sense?
Yes, but the radius of the nucleus would change. So would that affect the radius of
Little
the?
bit, yeah. Small changes will be there. There will be a shift. They call that not only because of that, because the size of the nucleus also is going to be slightly different. So, but those differences are going to be so small. The reason why I say this is nucleus is about 10,000 times smaller than an atom, right? So those small changes will not matter, but to some degree, there will be some small differences, but not as big as you go from lithium to hydrogen. All right?
Okay.
Good questions to think about, of course. Any other questions before we move on? So this is how we can calculate the energies. So if somebody asks a question about what is the relative energies of helium plus 1s electron, hydrogen 1s electron, you know how to use this equation and quickly calculate this. Again, you don't have to memorize any of these equations, but what I request each one of you in the class is to write down a detailed notes of what we are learning here and then prepare for the exams, okay? You will be allowed to consult your notes during the exam. All the constants will be given to you. Okay? So it's a question of answering the question properly. That's all it is. All right, good. So the next question is, why doesn't Bohr's theory apply for helium, lithium, and beryllium elemental metals? Why does it work only for one electron systems? Can anyone give a thought about this? What is Bohr missing here?
Is it Pauli's principle?
Hmm?
Pauli's principle of the pairing of electrons?
Mhm. We'll talk about Pauli's exclusion. I mean, we have done this in Chem 1. We'll talk a little bit later, but there is a fundamental problem here. What happens when you go from hydrogen to helium? You have one electron
Electrons.
extra, right? In the same shell. So what happens when you have two electrons in the same shell? Do they attract or do they repel?
Repel.
Well,
They repel. So there is an electron-electron repulsion, which Bohr's theory does not take into account. So that is the reason why Bohr's theory does not work well when you have multi-electron systems. You see, I'm slowly jumping from 2 electrons to anything more than 1 electron. The Bohr's theory does not work because of the increased contributions from electron-electron repulsions. Okay, that is number one problem. The number two problem is Bohr made a fundamental mistake. Remember what Bohr said? If I know the electron, I can calculate the distance, right? In other words, Bohr says I can precisely estimate the position of an electron in a hydrogen atom. The second thing he said was I can also calculate the velocity of an electron, which implies Bohr is telling us you can also find the momentum of this particle, right? All right, these are all beautiful mathematical equations, but can you prove it experimentally? Can you think of somebody going inside an atom with a measuring tape and then look at the distance between the nucleus and the electron? No, we just have to assume that these equations are correct, right? Or if you want to measure the distance or between the nucleus and an electron in an atom, what's the first thing that you need to do?
Stop the electron?
Please keep in mind that all the space in an atom is dark. There's absolutely no light inside. So if you want to find something in a dark room, what's the first thing that you do? Intuitively, we turn the light on, right? To see what is there. But then when you turn the light on, that light in the form of energy will be absorbed by this electron, right? It might move to a different level or it might increase its speed in the same level. Two possibilities. It can either jump to the orbit number 2, or because you're supplying energy in the form of light, that energy will be absorbed by this electron to increase its velocity. When it increases its velocity, the momentum also changes. Momentum is nothing but mass times velocity. So, one of the greatest scientists who won the Nobel Prize for this argument was Heisenberg. I'm sure you must have heard about this Heisenberg's uncertainty principle, right? What he said was, once you turn the light on, whatever you measure will not be the same as when the atom was in dark. So there is no way you can find the exact position and the momentum of the particles simultaneously and precisely at any time. In other words, what he said was, if delta P is the uncertainty in the momentum of the particle, and if delta X is uncertainty in the position of the particle, right? This is the uncertainty in the momentum, and that's the uncertainty in the position. This should be always greater than h over 4 pi. In other words, the product of these uncertainties is a constant number. What does that tell you? It's just not a mathematical equation. It's telling you something very powerful. It says, if you know the delta P, or the momentum of the particle precisely, then you will not know the position of the particle precisely. On the other hand, if you know the position of the particle precisely, then you know the momentum of the particle precisely. It is for that reason Heisenberg put this, delta P times delta X is always greater than h over 4 pi. In other words, you will never be able to know the position and the momentum of a particle precisely and simultaneously. Watch my language very carefully. These two words combine, precision and accuracy, right? Accurately and simultaneously. You cannot measure them. You can measure them individually, but you will not be able to know the position and the momentum of the particle precisely and simultaneously. This led to the development of quantum mechanics, the Schrodinger's equation. So in other words, people said, we should get away the description of precise orbits. In other words, an orbit is not exactly a straight line there. So Schrodinger basically said, well, an orbit is an approximate representation of the most probable location of an electron, nothing beyond that. So in other words, the size here, the radius that we're talking about, is the radius where the probability of finding an electron is high. That means there is certain probability of finding an electron closer to the nucleus as well as away from the nucleus, but the probability is high when you are in the orbit. So this is why we have a very cloudy definition of an orbit. An orbit is not a precise, extremely beautifully drawn circles, but it is more like a cloud where the probability is maximum at this distance. But in other words, we're not telling that the electron always stays in that orbit. It can be slightly below or above. That positional uncertainties and momentum uncertainties led to the Schrodinger's equation. I'm not going to get into the theoretical derivations because that's all you will learn from PChem. So my job here is to give you a qualitative explanation of what this might be. So when people looked at the position and the momentum and the energies of the particles of electrons in various shells and subshells, they found out a very interesting observation. If you look at the wave function, all of you know about a wave function, right? How many of you have taken a PChem course? Quantum mechanics, no? All right. I'll give you maybe a simple explanation of what a wave function is. A wave function has 4 coordinate system, X, Y, and Z for the position, and there is a time coordinate too, the T. So a wave function is a mathematical function that lets you know the location of an electron as a function of position and the time. Okay? When you take these wave functions for a 1s electron, and if this is the distance here from the nucleus, so if you plot the wave function as a function of the distance between the nucleus, what you find is at a very far distance, the wave function is almost 0, but as you come close, it increases. All right? So this is for the 1s. And if you look at the wave function for the 2s electron as a function of distance, what you find is you find a position, there's a negative wave function, and then it increases. So it starts out negative here. Now, I need to explain to you what is a positive and what is a negative wave function. The positive and negative is explained like this. For example, if I have a wave, I have a positive displacement and a negative displacement, right? So you can have a positive and a negative here. And in the middle, you have a point where the wave function is 0. That point where the wave function is 0 is what is called a node. Okay, so left of the node you have a positive and you have a negative. The reason why this becomes very important is if you are bringing two electrons, electron 1 and electron 2, if you are combining two electrons, you have to make sure that the positive and the positive are on the same side, negative and the negative on the same side. When you have the wave functions which are in phase, this combination of the wave functions gives you what we call a constructive wave. On the other hand, if you were to combine a wave see this waves here. One is positive, one is negative here. If you combine two electrons with completely out of phase wave functions, the combination leads to what we call a destructive combination. So this is constructive and that's destructive. Here again, one more thing I would like to let you know, that the positive and negative does not mean that you have increased electron density here and a decreased electron density there. This is a common misconception we have. The reason why this happens is because this contradicts our day-to-day observations. If you go to a beach, you have a wave, right? An up and a down. So basically, if you see the crest of a wave is accumulation of more water, and if you see a trough, you see a depletion of water. But that's not what happens in an electron functions. In fact, this is just only a phase. The probability, however, is related to chi-squared. So the probability of finding an electron is defined by the square of the wave function, not the wave function. So if you take the square of this wave function here, you get something like this. So the probability of finding an electron here is as good as probability of finding an electron here too, because it's not the sign, but it's a square. So even if you have a negative value, when you square it becomes a positive. So this is something that we have to keep in mind. Am I making sense here, folks? The wave functions, the general tutorial, how to interpret that and why wave functions are important in our understanding. That's about 1 hour 15 minutes time, folks. And we will. What I will do is I'll do over the next couple of days more voice or presentations, just like we have done for the nuclear reactions. And I'll let you play with this. And then next Wednesday again, this is what we decided, right? We'll meet once a week. Is that correct? Yeah. But if you have any questions, don't feel shy. Just send me an email. Those of you who have been sending emails to me, you know that I respond as quickly as possible because I care about your learning needs and make sure that whatever I can facilitate, I'll try to do that for you. And if those of you who want to have a private time, that say, Chari, I want to get a little bit more information, send me an email and we can set up a Zoom call, you know, at a time convenient for you. If it has to be over a weekend, so be it, I don't care. Okay, I can always find time for you because there is nothing more important for me in this job than attending to your needs. I don't care about the administration. Even if they call me for a meeting, I'll say I'm busy with students. All right, that is the kind of priority I give you. Some of you have taken classes, know this already from me. I make sure that you get the most attention, not the administrations. All right, folks. So with that, we'll close the show. You go back now, read the chapter one more time and start brushing up your basics on the electron configurations, electronegativities, and ionization energies. You know, we'll talk about that something a little bit in more detail as we go through the chapters. We'll talk about Slater's rules, effective nuclear charges, and all that stuff. So that will be an extension of what we have just learned. So I hope to see you all next Wednesday. And once we finish at least a couple of chapters, then we can think of having an exam. All right. So it will not be for next 3-4 weeks, but it doesn't mean that you should take it easy. I want you to pay attention because this is not something that you will learn in just one night. You will know that very soon as we start building up the material. All right. So have a great day and stay safe. Wash your hands, maintain social distancing, and you know, you can't afford to get sick. All right, with that, we'll talk next week.
I have a quick
Thank you,
question.
Dr. Char.
Yes.
Can you send us the PDF of the derivation you did? Because at the beginning, I couldn't really see the derivation that you did on the board. Can you send a PDF of it?
Gurveer, but you recorded the talk, right? You recorded the presentation.
Yes,
right?
I did. I have.
Yeah, that should be good, right?
Yes.
Yeah, so that's as good as a PDF.
Okay, I'll send it to you there.
Yeah, you can send it to me and then I'll upload it again into the class. So everybody will have a chance to read it again.
Okay, thank you.
How would you send it? You send me as a YouTube link or is that?
I think I'm gonna share it on the drive so you can download it on your computer.
Or can you turn that into YouTube video and send it to me?
Yes.
A link to the YouTube so that I can put the link in the.
Okay.
Yeah.
Okay. Yes.
So if you can do that over the semester, I'll appreciate Gurveer.
Okay. No problem.
Thank you very much.
Okay. Bye-bye.
All right, folks. Michael, Alyssa, Austin, all of you, have a great